Hello folks, welcome to the second video in the exponents and powers chapter. Today we're going to be talking about two things. I want to talk about powers of base 10 and why or how we might use them. But before I do, I have to talk about what is known as the zero exponent, or in other words, what happens when I put a power to the exponent of 0. So in order to understand what happens when I take a power, so say 3, and I put it to the exponent 0, what that gives me, let's first look at some powers that we do know how to evaluate. So here are some examples of some powers we know how to do. 5 to the power 3, and 3 to the power 3, 5 to the 2, 3 to the 2, and so on and so on. So again, when we say write it out in standard form, what we're talking about is what's the answer after I do that repeated multiplication. So 5 to the power 3 is 5 times 5 times 5, which is 125. 5 to the power 2 is 25. And 5 to the power 1 is simply just 5. And again, if we look at 3, 3 to the power 3 is 27. 3 to the power 2 is 9. And 3 to the power 1 is 3. So the question now is, what is 5 to the 0 and 3 to the 0? And this is something that we do a lot in math, is we look at something we know how to do, and then we establish a pattern that allows us to do something that maybe we didn't know how to do beforehand. So what is 5 to the power 3 as a repeated multiplication? Well, we know that it's 5 times 5 times 5, right? So it's 5 times 5 times 5, and then 5 to the power 2 is 5 times 5, and 5 to the power 1 is simply just 5. So what's happening each time? Well, in each of these cases, we are losing a 5, right? There's 3 of them, and then there's 2 of them, and then there's 1 of them. So in the final case, there's no more 5s. So you might initially think that means that the answer should be 0. And that's a fair assumption, but that's not quite what's happening. We have to consider what it means to lose a 5 in this case. And in this case, what it means to lose a 5 is we're not taking away 5 like we would if we were multiplying, right? So if I think about multiplying, 5 times 3 is 15, and then 5 times 2 is 10, and then 5 times 1 is 5. And what's happening each time is we are going down by 5, right? 15 minus 5 is 10, and then minus 5 is 5. So then 5 times 0 is 0, because again, we minus 5. But that's not what's happening in this example. 125 minus 5 is not 25. 125 divided by 5, right? So what's happening to go from 3 5s down to 2 5s in this case is we're dividing by 5. And then to go from 2 5s to 1 5, again, we're dividing by another 5. So if the pattern holds true, so exponent 3 means I have 3 5s. Exponent 2 means I have 2 5s because I divided one of the 5s away. Exponent 1 means I have 1 5 because I divided one of the 5s away. Exponent 0 means I have no 5s, but in this case, it's because I'm dividing one of those 5s away. And what is 5 divided by 5? Well, it's 1. And if we look at the same thing over here, it looks like there's a similar pattern happening, right? 3 to the power 3 is 3 times 3 times 3. And 3 to the power 2 is 3 times 3. And 3 to the power 1 is simply just 3. So again, what's happening is we're losing a 3 because it's being divided. So 27 divided by 3 is 9. And 9 divided by 3 is 3. So then 3 divided by 3 is, again, 1. And we hopefully notice something happening here, where if I take 5 and I put it to the power 0, I get 1. And if I take 3 and I put it to the power 0, I also get 1. So what that means is that in general, if I take any number, so in this case here, n, where n is some integer, right? It could be any number we want it to be. 0 other than 0, right? So 0 to the 0 is a weird one, but it can be 1, it can be 2, it can be 3, 4, 5, 6, 7. It does not matter. If I take that n and I put it to the power 0, my result is always going to be 1. Okay? So let's take a look at a couple of examples. So if I wanted to do 4 to the power 0, well, simply enough, that is equal to 1. Now, be careful, just like with the last video where we were talking about negative bases, we first have to determine what the base is. So if I'm looking at part B, I have to think about what my base is. And if I'm looking at part C, I have to think about what my base is. And again, if we're thinking back to the last video, the base can be found if the negative is inside the bracket or not. So for question B here, my base is not -4. My base is simply just 4 because it's not inside that bracket. So if I had a power that wasn't 0 and I'm thinking about whether or not that negative gets repeated, in this case it wouldn't because the negative isn't inside the bracket. But for question C here, the negative is inside the bracket. So in this case, the base is -4. So what does that mean? It means, again, the order in which I apply these powers. So for question B, I'm going to do 4 to the power 0 first, and I get the negative that was not touched yet, and then I get the result 1. So the answer here is -1. Whereas for question C, I'm going to deal with the negative, so I get -4, and then I put that to the power 0. And again, from my rule from previously, any number, whether it's positive or negative, if I put that number to the power 0, I always get 1. Okay, so question B, the negative is not being put to the power. It's not a part of my base, so we're going to deal with it after I've done the exponent. In question C, the negative is a part of my base, so whatever rules that I have to apply to that negative as well. Okay, so why do we care about 0 powers? Well, for a couple of reasons. Again, just like what I was talking about in the last video, is eventually you're going to move on and you're going to be asked to do more stuff with more things, and understanding that a power 0 equals 1 is really important. But it also helps us understand this concept of powers of base 10, because that's how we learn numbers. We learn numbers as powers of 10. So if I just gave you the number 3,452, right, we should hopefully be able to recognize that as 3 groups of 1,000, 4 groups of hundreds. I don't know why I put squared there, thousands. I meant to put an S. 1,000, 3 thousands, 4 hundreds, and then 5 tens, and then finally 2 ones. Right? So it's 3 groups of 1,000, and it's 4 groups of 100, and it's 5 groups of 10, and it's 2 groups of 1, and then I can simply add those together to get this idea of 3,452. And the reason that understanding numbers in this way can be useful is it lets me do mental math in a different way, because now instead of trying to do 3,000 times something, I can simply just think of it as 3 times something, but then recognize how the tens are going to interact with one another. It also allows me to think about other number systems. So when I'm thinking about numbers in base 10, that's great, but I could be thinking about numbers in base 2 or base 3. And there's reasons we might want to do that. So if you think about like binary, something that computers use, right, that is a base 2 number system. So what does this mean in terms of, what do I mean when I say powers of 10? Well, all of these numbers, these 1,000 and 100 and 10 and even 1, they can be written as a power with base 10. So what does that look like? Well, what is 1,000 as a power of base 10? It's 10 with an exponent 3. And what is 100 with a power of base 10? Well, it's 10 with an exponent 2. And what is 10 to a power of base 10? Again, this is something we talked about in the last video, where it's only 110, so it's generally just 10 to the 1. And then finally, 1 as a power of base 10, again, is something we just talked about in this video. It's 10 to the power 0. So I can think about a number like 3,452 as its digits and its powers of base 10. So this thing can be written as 3 times 10 to the 3 plus 4 times 10 to the 2 plus 5 times 10 to the 1, and then finally plus 2 times 10 to the 0. And if you're unconvinced, like, go backwards, right? So grab a calculator and actually do this work in your calculator and see what you get. So 3 times 10 to the 3 is 1,000, and 4 times 10 to the 2 is 100, and 5 times 10 to the 1 is 10, and then finally 2 times 10 to the 0 is 1. And then 3 times 1,000 is 3,000, and 4 times 100 is 400. 5 times 10 is 50, and 2 times 1 is 2. And now I add it all together and I get 3,452, the number I started with. Okay, so when I'm talking about writing something out as powers of base 10, if you see it on an assignment or something, this is what I'm talking about. I'm talking about breaking the number up into its place, right? It's ones, it's tens, it's hundreds, it's thousands, it's 10,000s, 100,000s, and so on. But instead of writing them out as those words, write them out as powers with base 10 and whatever exponent is necessary. Again, there's a nice little pattern here. If you're starting from right to left, you always start at 0 and you simply just count up. So 0, 1, 2, 3. The next one would be 10,000. That's 10 to the 4. And then 100,000 would be 10 to the 5. And so on and so on and so on. All right, just as a quick little bonus segment here, I talked about it earlier, but I could also write things out as powers of base 2, which we know as binary. And what that asks you to do, so if I wanted to do the number 111 as powers of base 10, well, what that means, it's 1 times 10 to the 2 plus 1 times 10 to the 1 plus 1 times 10 to the 0. But if I wanted to think about it not as base 10, but as something else like base 2 or base 3, so binary uses ones and zeros, because instead of working from digits 0 through 9 and using base 10, it works with the number digits 0 through 1, and it uses base 2. So 111 in binary would be 1 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. And if I wanted to then convert that to powers of base 10, I simply just have to do these multiplications and additions. So 2 times 2 is 4, so this is 1 times 4. And 2 times 1 is 2, so this is 1 times 2. And then 2 to the 0 is 1, so this is 1 times 1. So we get 4 plus 2 plus 1, which is 7. So in powers of base 10, the number 111 is 111, but in powers of base 2, the number 111 would actually be 7. All right, nice little bonus there. Okay, see you all in the next video.